Yo, if you'd like to support me and this channel, Moof University, in creating more video tutorials, then please consider making a financial contribution at my website, moofuniversity.com. Thank you and enjoy the video.
Okay, so enzyme inhibition, specifically competitive inhibitors. We've talked about them before, but I want to talk about them more completely here. So we know that a free enzyme and a substrate can come together to form the enzyme-substrate complex, which goes towards enzyme and product. So here I've drawn a free enzyme with an active site, sort of like with a square shape. Right, so this here is the active site, and that's of course where the substrate binds to give the enzyme-substrate complex. Now, competitive inhibitors, they compete with the substrate for binding at the active site. So we would expect a competitive inhibitor, labeled here as IC, I for inhibitor, C for competitive, to have a shape that's similar, right? So if we put the substrate as a square, the competitive inhibitor, square-shaped, would fit into that active site to form the enzyme inhibitor complex, which of course cannot make product. This enzyme is now inhibited. Now, because the substrate and the inhibitor both bind at the active site, or both try to bind at the active site, the enzyme can only bind one or the other. So the competitive inhibitor can only bind free enzyme. So let's look at this a little bit differently. So the enzyme can only bind one of them. So either the enzyme-substrate complex will form, or the enzyme-competitive inhibitor complex will form. We cannot form an enzyme-substrate inhibitor complex or competitive inhibitor complex. So there's no ESI, not in this case at least, because they can't both bind the active site at the same time. So this enzyme can either bind the substrate to form the enzyme-substrate complex, or the enzyme can bind the competitive inhibitor to form the enzyme-competitive inhibitor complex. And of course, if that happens, if we have the enzyme bound by the competitive inhibitor, that is the inhibited enzyme. That enzyme cannot give you product. And of course, the substrate cannot bind the enzyme while the competitive inhibitor is bound. That's an important idea to stress. And because of that, because the substrate can't bind the enzyme when the inhibitor is bound, what does that do to affinity? Well, the enzyme's affinity for the substrate. Well, if the competitive inhibitor's presence makes it so that the substrate can't bind, that must mean that the enzyme has a reduced affinity. And this actually has an important effect, because that increases the apparent KM. Now, what about VMAX though? We've talked about this before, about how if you, well, maybe I shouldn't say that, because what if you are only watching this video and not the other one? The idea here is that we could take substrate, and if the concentration is high enough, and they can displace the competitive inhibitor that's attached to the enzyme to give you the enzyme-substrate complex. So that's what this is here, going from substrate, knocking off that competitive inhibitor to form the enzyme-substrate complex. This can happen if there's a lot of substrate. If you imagine this as a sort of game of musical chairs, let's just imagine there are 10 chairs, and there are maybe 6 enzymes and 6 inhibitors. They both pretty much have an equal chance of sitting down on one of those chairs, which each represent the enzyme's active site. But if there are, just for the sake of this example, if there are 5 chairs, 5 enzymes, right, 5 enzyme active sites, and there are 100 substrates and only 1 inhibitor, it's much, much, much more likely that a substrate will sit in one of those chairs or bind one of those active sites than a competitive inhibitor will. So in essence, we could take those substrates, displace these inhibitors, and create the enzyme-substrate complex at the same rate as we would if this inhibitor wasn't there. That's, again, assuming the substrate concentration is high enough. So what that means is that the Vmax can still be reached, because the enzyme-substrate complex can form and proceed towards products just as quickly as it could without this inhibitor, if the substrate concentration is so high that it basically negates the effect of the competitive inhibitor. So how does that look on the hyperbolic graph? Well, with this yellow line here, I've drawn the line with no inhibitor, and the pink line with a competitive inhibitor. We're plotting, of course, reaction velocity versus substrate concentration. So the yellow line here reaches a Vmax of 100, and of course these units are concentration units over time. I didn't give specific units in this case just for the sake of simplicity. So up here, this maximum velocity is Vmax for the yellow line. And we said that with a competitive inhibitor we could still reach that Vmax if the concentration of substrate is high enough. So you can probably see that this pink line here is sort of approaching Vmax. If we increased the substrate concentration even further, maybe to a point out here or something, maybe at that substrate concentration we might actually reach the Vmax, right? So the Vmax of this pink line and the Vmax of this yellow line, right, with or without an inhibitor, these values of Vmax are equal. These are equal values. Now, what if we go to half the Vmax? So if we originally had 100 for the Vmax. If we go down to 50, that's Vmax over 2. The substrate concentration at Vmax over 2 is the Km. So if we look at the yellow line, its Km is the substrate concentration at half of the Vmax, which is down here. So this is the Km of the uninhibited reaction, of the uninhibited enzyme. But if we notice for this pink line, to get to that same Vmax over 2, right? And I'll even label that here. So this is Vmax over 2 for both cases. To reach that same Vmax over 2, we need a higher substrate concentration. So this is Km of the inhibited enzyme. So sometimes people call this Km apparent. And you can see that it's larger than the original Km, right? So this Km apparent is larger than that original Km. Now how does this translate into the Lineweaver-Burk plot? So what we have here in orange is the equation, the y equals mx plus b line for the Lineweaver-Burk plot. And of course, here is the y-intercept, which we know is equal to 1 over the Vmax. And here we have x-intercepts of these two graphs. Again, yellow, no inhibitor, pink with competitive inhibitor. So we notice that the y-intercept for both of those graphs is the same. It doesn't change. So the yellow one is the uninhibited reaction, and the pink one is the inhibited reaction, but the y-intercept doesn't change. Why is that? Well, the y-intercept is equal to 1 over the Vmax, and the Vmax did not change. So it makes sense that the y-intercept does not change. Now, the x-intercept did change. The original one here, with no inhibitor, we'll call that x-intercept 1, and then over here, we've got x-intercept 2 for the pink inhibited reaction, x-intercept 2. So we can see that the x-intercept 1 is further left, and the x-intercept 2 is further right. Why is that? Well, the x-intercept is equal to negative 1 over the Km, and we know the Km changed. The Km increased. So x-intercept equals negative 1 over the Km. Now, if Km increased, that means the x-intercept is going to be smaller. If we're dividing by a bigger Km, we're going to have a smaller x-intercept. And of course, that's smaller in magnitude, right? So in terms of its distance away from 0. So here, x-intercept number 1, let's just say for the sake of this example, and simplicity's sake, that this was like negative 5, right? X-intercept 2, since it's closer to 0, right, closer to x equals 0, right, 0 here, closer to 0, 0, let's just say that that's like negative 2, right? It's a smaller magnitude and closer to 0. So that x-intercept is closer to 0. A larger Km brings that x-intercept closer to 0. And that, of course, also has an effect on the slope. The slope is equal to m, which is Km over the Vmax, and we can see that over here. Km over Vmax. So again, the Vmax did not change, so we could just say that this value, just didn't change. It's the same value. But the Km increased, so we have a bigger number in the numerator and the same number in the denominator. So what does that do to our slope? well, we're taking a bigger number divided by the same Vmax, that means our slope is going to increase, right? The slope increased, which is why the pink line is at a higher slope than the original yellow line. Okay. So I hope that video was helpful. Thank you for watching.
Yo, if you found that video helpful, then please be sure to like, comment, and subscribe for more content. And if you know anybody who might find this video helpful, then please be sure to share it with them. Thank you and happy studying.